And now I'll just introduce Ken Potter. He's a retired professor at the Civil and Environmental Engineering Department at the University of Wisconsin-Madison, talking about flooding and some flooding solutions today. So I'll turn it over to Ken. Ken, you can just let me know when you'd like me to advance the slides.
Will do. Thank you, Paul. Well, it's a great pleasure to talk to you today. I wish I could be there in person. Let me just say that my email address is kwpotter@wisc.edu. So if you don't get all your questions answered, or you have some other thing you want to talk about for your own situation, just feel free to give me an email. This photo you see there was taken from a small camera up on a balloon, and this is flooding that occurred 2 summers ago in just on the west side of Madison in Middleton, those of you that have been down in this area. And it results from the South Fork of Pheasant Branch Creek, and it was quite extensive. Okay, next slide. Now, flooding is not a very complicated thing, okay? What's complicated is human behavior, but flooding itself is really straightforward. And you all know this. So liquid water moves downwards. It either goes into the ground or down slope. And if it moves more slowly than it's supplied, that water ponds, and that's what a flood is, ponding water because it can't move downhill or down into the ground. Water moving into the ground can be impeded by an impervious surface, of which there are a lot when we develop land, so a concrete parking lot. But we also often compact soils, and compacted soils can be almost as impermeable as concrete. Also, if water moving downward hits the water table, the groundwater table, then you can also have flooding. And that's an emerging issue. We're having a lot more problems with water tables rising, and I'm going to discuss that towards the end of the talk. Now, water moving on the surface often ends up in pipes or channels, and if those pipes or channels can't convey that water, again, you get water backing up, ponding, and potentially have flooding. Next slide. Flooding in Wisconsin is increasing, and 2 reasons. One is climate change, and there's really good evidence that rainfalls are increasing in intensity and amount in the last couple of decades, and will continue to increase. And it's for the simple reason that warm air can hold more water. And then the second factor, the one I'm focusing on today, is land development, and really impervious surfaces and also compacted soils are the real problem there. And we really need to make sure that new development doesn't increase flood risk. And we also have to go back to places that were already developed and see if we can retrofit. Next slide. We can actually fix compaction, and we can do that by enhancing the soil, and I'll talk about that later in the talk. And another thing I'm going to mention later in the talk is that everything's interconnected. We have watersheds at all scales. Water's moving downward, and it ends up in the Gulf of Mexico. I actually grew up in New Orleans, so the water we produce here goes all the way down to New Orleans. It could cause flooding there. And we have to understand these watersheds at different scales and recognize that what we do at our scale is going to affect people downstream. Next slide. Okay, so I'm going to talk about 3 kinds of flooding. First, lake flooding. And the one important thing about lake flooding that you need to understand is that many lakes drain very slowly. Think about a wash basin that got clogged, how easily that could overflow. And so in that case, it's not the rate of runoff, it's how much water runs off. So for example, if you have a lot of times, in fact, most cities have a pond that's dry that will temporarily hold water and then release it within 24 hours. Well, that has no benefit to the lake because delaying it by a few hours isn't going to matter. It's that amount of water because the lake drains so slowly. Now with stream flooding, the peak rate does matter as well as the amount of runoff. Next slide. Okay, so local flooding in developed areas is going to be exceeded by extreme rainfalls that exceed the capacity of the drainage system. And by the way, a lot of times if the water's draining into a lake, that drainage system can back up. So that's a big problem in East Madison. And in fact, the city of Madison is now working on trying to deal with that. The fact that the storm drains flowing out of the Yahara River below Lake Mendota are being impeded by, or the water's rising in the Yahara and backing up those storm sewers. So that's an issue. And then there's the rising groundwater, which is an emerging problem. Okay, next slide. Okay, here's some data. So I've been working, putting a lot of my effort into the Yahara lakes, but what you're hearing about the lakes, the Yahara lakes, is going to apply to any lake that drains relatively slowly. And the Yahara lakes drain slowly because the Yahara River below Lake Monona only drops a few inches per mile, so it's a very slow drainage. So what we have here are annual maximum water levels. They're on the same scale. So you can see Mendota's the upstream lake, and it's at above 850 feet. And then Lake Monona is downstream of Lake Mendota, so it's at a lower level. Mendota's been steadily increasing all the way from 1920. Interestingly, Lake Monona decreased up until the late 60s, early 70s, and then started increasing. And that's kind of an interesting pattern there. But that actually was because as development occurred, there was flooding occurring in Lake Monona. And so Mendota was managed as a flood control reservoir. And so it increased, Mendota increased for two reasons. One is development in its watershed, and then development in the Monona watershed. But when a new lake manager came in, then that turned around and Monona started flooding. And now Monona actually has a more serious problem. And again, you can see the recent floods, 93, 2000, 2008, 2018. Next slide. Okay, so urbanization significantly increases the amount of runoff, the rate of runoff, and therefore it increases the risk of lake and stream flooding. And the big issues are the impervious surfaces, the compacted soil, and then the fact that we expedite drainage. We move the drainage out quickly so that we reduce the upstream flooding, but that increases flooding in the lakes. Next slide. Okay, this is a map of showing urban development. So that's the Yahara Lakes watershed, the entire lakes watershed. So you can see the northernmost lake is Lake Mendota. That's at the highest level. Water then flows into Monona, and so on and so forth. In 1970, that's the blue. And then by 2017, that's the urban expansion. And you can see there's quite a bit of it. And there's been some more, obviously, in the last 3 years. So, but the real take-home thing is if you look at the drainage area to Lake Mendota, it's largely undeveloped. It's probably only around 10 to 15% right now developed. So there's a lot of future development, and yet there's already been enough development to increase flood risk. So that's a challenge. Okay, so there's a question from Michael. And I can't read the whole question, so.
Yep. He said, to what extent is flooding in the Madison area due to the relative lack of relief, hence little difference in elevation between the lakes?
Yeah, that's exactly right. That's the issue. The slow drainage rate out of Lake Monona is due to the lack of relief down to the lower lakes. So that's the problem. So when you have lakes that drain slowly, then they have flooding issues that depend on the amount of runoff as well as the peak. Okay, next slide. Now, another important facet of this problem is that in the glaciated part of North America and in glaciated areas around the world, you can have what we call internally drained areas. They're areas where there's no surface drainage. And they resulted from the fact that these glaciers, which were 1,000 feet of ice up above, when they melted, well, first place, when they moved, they obviously gouged a lot of sediment. They moved a lot of sediment around. And then when they melted, a lot of the sediment blocked headwaters of many streams. and that left these areas that for the most part never no water is released via surface except in real extreme floods. Actually, there's a map for the whole county now, and I haven't been able to get it in a presentation form. But if anybody's interested, I can show you where to get that. That shows the internally drained areas for the entire county, and you're going to have the same issues in other parts of the state. These internally drained areas, and they're really problematic because you talk about slow drainage. If you increase the runoff to the lowest parts of these systems, and there may or may not be a pond there, you're going to cause that area to have a pond, and then that pond that's going to expand. And so they're really problematic. They only lose water by evaporation and seepage. And so they're of special importance, and they're all over the glaciated North America. Next slide. Okay, this is a demonstration of what happens when you drain an internally drained area. So on the west side of Madison, there's a Pheasant Branch, and Pheasant Branch has a fork that heads south, and then there's a fork, there's a north fork that heads south, and then a south fork that heads north, and they actually come together in that slide that was the first slide that I showed you, the cover slide. That was pretty much at the junction of those two streams. And there was a fairly large internally drained area in the South Fork. It was like 20% of that watershed that Madison developed, because it was in Madison. And then they actually connected that previously closed area to the South Fork because they were significantly increasing the amount of runoff. And that caused, therefore, a great increase in the amount of runoff. And this slide shows that. So what we have here is the ratio of the storm flow. And so by storm flow, I mean the flow in the stream that's a result of a storm rather than what's coming out of groundwater. I have the ratio of the Pheasant Branch, the South Fork. Actually, this is for the whole Pheasant Branch, to that of the flow in Black Earth Creek, which is a stream that flows west out of Madison, which has very little development in it. And what you can see is that if you look at that ratio, exactly at the time when the development occurred, there's a huge uptick in that ratio, and that's a doubling, almost a doubling of the amount of water in the stream. So that kind of demonstrates what we already knew, but it's always nice to get some data. Next slide. Okay, so how can we deal with the impervious surfaces? We have to find a way we're going to have impervious surfaces. We don't want it raining in our house, right? And so we're going to have streets. Muddy streets don't work. In fact, they would be relatively impervious anyway. So we have to have some way to put water in the ground at a rate much higher than would normally happen, say, in just a green area. So we have a variety of strategies that we can do that with. These are actually required by the Wisconsin Department of Natural Resources based on regulations in 2002. That is, the volume of runoff from a new development had to be maintained at 90% of what it was before. And that requirement was actually passed down from a federal requirement in the Clean Water Act, which was actually designed not to prevent flooding, but was designed to prevent stream erosion. Clean Water Act was a water quality act. And so if you increase the amount of storm flow, and particularly the duration of storm flow, you're going to cause stream erosion. And that's happened in every major city in the world. I went to grad school in Baltimore, and there was a huge amount of stream erosion there when Baltimore developed. So anyway, the volume control was required to deal with that. It was simply an erosion issue and had nothing to do with the lakes. Okay. Next slide. So those DNR requirements are insufficient. They only require that you have maintained 90% of what didn't run off. And so they allow they basically allow a 10% decrease in that water that doesn't run off. And we call that water the stay on, okay, the stay on. And the stay on is a big number. Just to give you a rough idea, roughly 30 inches of rainfall, actually a little higher, but just to make the math easier. Of that 30, about 20 inches evaporates or transpires from plants, and another 8 inches would infiltrate the ground and would recharge groundwater. So it wouldn't evaporate, which would recharge groundwater. So there's not much left. We'd only have 3 inches left that would normally run off. And so if you allow an increase in the if you allow an increase in the amount of runoff, you're going to have a significant impact. Question: is the Great Basin
in the Western U.S. an example of an internal drainage area?
Yes. Yes. Lots of internally drained areas in the Western U.S. So anyway, this is a big problem. The fact that the ordinance, the DNR ordinance, only requires that you control 90%. It allows an increase in runoff that's significant, almost doubles it. Next slide. Now, I had the pleasure of chairing a committee a couple years ago. It was an outstanding committee. We had consultants, and we had representatives of the communities that were on major committees. We had DNR and so on and so forth. So we had a lot of good people on it, and they recommended, after over a year of meetings, they recommended 100% control of pre-development stay on. That is, no increase allowed in runoff. Now that's done for a particular year. It's kind of a moderate year, so in order to enforce an act, you have to have it very cleanly defined. So that's based on a particular year. And so we recommended to go to 100%, not 90%. Within a month of after our report was written, or a few months, the legislature, somebody stuck in 2 or 3 sentences in a bill, in an unrelated bill, and prohibited any local government from increasing the stay-on requirement that the DNR had, or from limiting, from enforcing a requirement that was more stringent than the DNR requirement, even though the DNR requirement had nothing to do with flooding. So anyway, so that really stopped progress in trying to prevent increases in runoff. Next slide. Now here's the impact that could have. So this is based on a modeling study that Nick Hayden, the grad student in my department, did. It's based on, we classify all the soils in the world, by the way, are classified by the NRCS as A, B, C, or D, and A soil being extremely permeable, the D soil being the least permeable. So there's kind of these 4 soil groups. And this is for a B soil, which is about what is the dominant soil in the Yahara watershed. And then it's using rainfall for the Yahara, upper Yahara, for the Lake Mendota. And it's actually using the transposed 2008 storm. One thing I did after the 2008 storm was to get a digital record of that rainfall, which caused a lot of flooding in Madison, but it really wasn't centered on the Mendota watershed. So we centered it on the Mendota watershed. So, and we call that storm transposition. It's a tool that's been used by hydrologists ever since the early 1900s, believe it or not. So it's an excellent tool. So we transposed that storm, and then the student modeled a new development. And here's the total amount of runoff in inches that you would have gotten for different requirements. So if you had 100% control, you'd have had an 8% increase in runoff. And you might say, why not a 0? And that's because the 100% control is for a specific year where you really didn't have an event as big as this one. So one would expect some increase, even though you have 100% control for that design year. If you went to 90% control, which is what the DNR requires, but which is, again, not a flood requirement, it had a 55% increase. And on the left, by the way, you can see what the pre-development runoff was. So that had a huge impact had the storm been transposed. And even if the storm had not been transposed, we did the modeling on that, and it would have had a huge impact. Next slide. So here's some of the strategies. Most of you are probably familiar with typical control strategies. On the upper left, we have a rain garden, a bioretention cell, whatever you want to call it. This one's in the street. Bottom left, anybody know what that building is? That's a roof garden. And that's Chicago City Hall. Really great. I'm increasingly supportive of doing things on the roof. It does require a little more expense in construction because you have to be able to handle the weight of the plants in the water, but it can be very, very effective in places where you'd have a hard time doing any kind of volume control. And then we can build hardscapes like up in the center, top center. That's one kind of hardscape that can have high infiltration rates. We can also have concrete or asphalt that has enormous infiltration rates. So they're basically the way they can make the asphalt or do the concrete. They can get 100 inches per hour or more when it's first put out. And even if it clogs up some, you still end up with enormous rates. Though there are ways of vacuuming these out, and when they're installed, there's usually a requirement that they be cleaned periodically. And on the bottom, you can see a parking lot that could have a porous asphalt surface, and then you could have a storage area underneath it. So you could also deal with the detention requirement. Top right, street. I'm trees in the street right away. I'm increasingly big on that. That can be very effective. And the bottom right is just another bioretention in a parking lot. Next slide. Now, another thing that's really effective is to deal with the compacted soils. And there's a method called subsoiling, which is based on deep tilling, chisel plowing, and adding compost. And actually, we had a guy here in town about 15 years ago named Yahara who had all kinds of great ideas for improving stormwater runoff control, both peak and volume and quality. And he was pushing this. And we've done some of this in Wisconsin, but I had a student, and I'm going to show you that in the next slide. I had a student do some, and actually it was his idea, so I just helped. He did, and this is Jeremy Belusik. He also works for the county today. He had these test plots, and you can see the plots on the left, and then on the right you can see how he measured the flows coming off of them. So that white pipe drains that plot, which slopes that way, and then there's a bucket there, and that bucket, as one side fills, then there's a message recorded on a sensor, and so it's like a tipping bucket tipping bucket for rain capture. So anyway, that was the design, and then what he did was he sprinkled water at a known rate on each one of these, and he did various practices. So next slide. So these are the results, and it basically shows the reduction in surface runoff. He had his sprinkling test shown here, 2.2 inches in 30 minutes. The control was the percent of runoff, so it was 7% runoff for that particular test. He had various tests. If you did the deep tilling alone, he cut it in half. Chisel plowing, he went down further, and then if you added compost, you had practically nothing. So all three of those can be done. After that, we did a certain amount of this here in town, but I passed this MS report on to some former colleagues of mine when I was in grad school, and they were in Maryland, and they have really gone gangbuster with that. So they're now requiring deep tilling everywhere, and subsoiling is what they call it. Next slide. And here's an example of how they do it. Some pretty big equipment, and I'm not showing you all the steps, but basically they really redo down to a foot or so that soil, and then add compost, and it's extremely effective. Next slide. Okay. So anyway, that's something I think we got to work on. And I'm actually I've been a volunteer on a committee with Middleton for quite a long time. Cost figures. What does it cost? It's the good thing about subsoiling is that, we're going to try to do this in Middleton. And so, as I said, when I first came here in '79, within a year I was on the Middleton Water Resource Commission because I lived for a few months in Middleton, and I've been on that commission ever since. I'm still on it, and so I learned a lot about how all this works in the real world, and we're going to be doing some demonstrations of that. But the key to keeping the cost down is if you do a development, the way we deal with infiltration now is the developer plans to have infiltration devices downstream of all the houses, pretty much. Nothing's done on the houses. We're looking to require that each house subsoil the route that water coming off the roof takes to the street. Okay, so if you have 4 downspouts, for example, every one of them is going to have a pathway that's only going to be a few feet wide and variable lengths depending on whether it's front of the house or the back. But anyway, it'd be a small fraction of the total yard. If you subsoil that, it's about as effective as you could get. It could pretty much do 100% control very easily. And so the cost of that wouldn't be too high. And I don't really have the numbers. We're going to get an idea, I think, when we do the tests here in the next year. We'll get an idea of what costs are. But we're hoping to change our requirements. And it's a little tricky because the requirements for stormwater management go on the whole plat, the whole development, rather than on individual houses. So we're going to be requiring something that's done after the house is designed so that you know where the downspouts are. So that's going to be a little tricky. Next slide. Now, the reason that our 100% control was blocked by the legislature was the fear that it was going to be costly, that it was going to raise the cost of a house, and people weren't going to want to live in Madison. They're going to or in the Madison area, they're going to move out further, and from an environmental point of view, that's even worse. And so the way we dealt with that was to say that we would have a form of pollution trading. And I'm not sure how many of you are familiar with it, but if you remember 20 years, 30 years ago, we had acid rain, acid deposition. And I remember going to grad school out in California, and nobody could exercise in the afternoon. The smog was so bad. And we've really done a good job in this country taking care of sulfur and nitrogen oxides. And we did that by trading, basically. So power plants that couldn't economically meet the standard, if there was a power plant nearby in the same airshed that could and overcompensate, then there would be money exchanged. Okay, so that's the way that worked. And that's been very effective. When I came to Wisconsin, about that time, there was a real problem on the Wisconsin and Fox Rivers with biological oxygen demand, which is abbreviated BOD, and that's the demand for oxygen that occurs when organic matter is dumped into a stream. And there are a lot of paper mills, as you know, that drain into the Wisconsin and Fox Rivers, and they're discharging organic materials which have a high biological oxygen demand. For those waste to break down, they use a lot of oxygen. And so the state enacted regulations where the permitted amount of pollution that could be put in the stream, how much of this organic matter was dependent on the temperature and the flow, because obviously the warmer the water, the more problems you have with oxygen, and the lower the flow, the more problems you have. So the regulations based on both flow and temperature, but it allowed trading, and therefore the cost was done in the most efficient way possible. We're also doing that with phosphorus control. We've in the last couple of years, we've been meeting the federal requirements on phosphorus We have a TMDL here, and we've been meeting that using trading. As long as the idea is you control the phosphorus in the places where it's most cost effective, and you over control there, and therefore you don't have to do as much in other places. And that's been exceedingly effective. And I woke up in the middle of the night last night thinking about this, believe it or not, and just frustrated that we could do such a good job on phosphorus, because our lakes are really a lot cleaner than they were. And we're getting better. We can do such a good job with that, and yet we can't do the same job with flooding, which doesn't make any sense. Next slide. Okay, there's some key interrelationships in flooding. Remember, I told you it's a watershed deal. It's as you get to larger and larger watersheds, you have impacts that are coming from upstream, and so there's a lot of interrelationships in the hydrology. So you can get high lake levels. High lake levels themselves can actually raise the water table in the adjacent groundwater, and that can cause flooding on the land. And I know some people living in Monona that have, they don't have deep basements, they have really shallow basements. So some of them have sumps going on 24 hours a day, pumping water back into Monona, which then flows back to the sumps and back. So it's kind of ridiculous. So anyway, that's something that you really don't want to be doing. You're wasting a lot of energy. Another problem is that almost always when you have a flooding problem at a really small scale, you almost always end up putting water or creating a potential problem downstream. And so I think cities are getting better at recognizing that. And often you're sending it to another municipality. And that happened in Madison. We had some of our closed depressions flooded 2 years ago. And the solutions are to pump more water out of them after an event. And that water actually is going to go from Middleton to Madison. So we've got to be real careful and cooperate with the other agencies, the other units of government when we do that. Another thing that's really important to recognize is that infiltration practices near lakes that are volume sensitive are not really helping the volume control. And so if you're working with a lake that drains slowly and there's a new construction, taking the water from the roof and putting it into the ground, it's not going to really help you in terms of the volume of water that gets to the lake, though you are improving water quality, so it does have some benefit. Next slide. Now, one thing we're beginning to see much more common is groundwater flooding. And actually, it's not a totally new thing. When I came here 35 years ago, there was groundwater flooding in the northern part of the Yahara watershed. But it was affecting trailer homes and so on and so forth. So nobody really they couldn't raise enough awareness to have any change there. But anyway, groundwater levels have been rising over the last 30 years, and especially in the last decade. And so they can be a real problem. And they're most common in internally drained areas, but they do occur in other places. Next slide. Now, the bad thing about groundwater flooding is that you don't really discover those for the most part until after you have a problem. And in recent years, we're finding lots of, particularly some of the smaller towns, where they're having extensive increases in the water table, and there's no easy fix for that. So we really got to try to get on top of that. And so one of the things I've been pushing with the Geological and Natural History survey here, and I think they're going to move on this, is to try to anticipate where we might have groundwater flooding in the future, so that we don't exacerbate that by putting runoff, infiltrating runoff there. Next slide. So what do we do? I mean, it's kind of bad. You know, we're going to get increases in rainfall. Groundwater is liable to rise in places. So how are we going to deal with those situations? And one thing we're going to have to do is make wiser use of vegetation. In a heavily vegetated area, as I mentioned before, about 2/3 of the annual precipitation evaporates or transpires. And most of the rest goes to groundwater, and meaning only about 10% runs off to the surface. Next slide. So wherever we have high groundwater tables, or where we anticipate high groundwater tables, we really have to go green. We have to vegetate as much as possible, and I think we need to find the optimal vegetation. And there's a lot of literature on this, and so we're not moving blindly. Willows, for example, and cottonwoods, or trees that have high evapotranspiration rates, and they can also handle wet conditions. So, because you could have years where the water table rises enough where we would kill other trees. So I think this is a really important problem, and we need to get help from the vegetation experts, and we've really got to green up, make a lot more use of transpiration as a way to deal with rainfall. Now, it's a closed system. Water is going to go somewhere, and so if we transpire it, it's going to go to Michigan, right, or someplace to the east. And so that's just one of the things we're going to have to deal with. And I actually, at a grander scale, I can see this country looking at finding ways of recharging depleted aquifers as one way to make use of the fact that we're going to have more rainfall. Next slide. Okay, so let me just summarize. Climate, land use change, they're increasing flood risk, and I really think it's a serious problem, and a lot of other people do. I know Madison's taking it seriously, Middleton's taking it seriously. Our current practices are generally insufficient, and sometimes we're actually increasing the risk and not knowing it. The City of Madison told me about a bioretention cell they had in the street not far from campus, where it seemed to be wet all the time, and it turned out that the homeowner that was closest to it was basically pumping water out of the basement and running it to this bioretention cell. So we had that bad situation again where we were just circulating water between the basement and the bioretention, and obviously that's not a good thing. And we really have to look at watersheds, think about watersheds at different scale, and you can't solve this problem just looking at the small scale. Next slide. So my biggest recommendation is we have to get rid of that legislative limit on volume control. And I'm giving a lot of talks, and I don't know if that's helping, but I think at some point we need to get the legislature to understand that with volume trading, we can do things very efficiently. And then if we don't do it, the cost is going to be much higher because of the flooding. The other thing is, and I don't have time to talk much about this, but as you know, many facilities are designed based on extreme rainfall rates. We generally use the NRCS estimates of probabilities of rainfalls of different durations. And those are out of date. And I have a colleague who's been working on this. He's got some good alternatives for the present standards we use. We're going to have to use standards that account for changes in the future, and that's really a high priority. Madison is dealing with this by simply going from the 100 to the 200-year event for many of its designs. But it really would be nice to make use of better tools, which I think the university is producing, to come up with tools that can tell us what the probabilities of certain rainfalls are in the future. And then you have to think about the life of the project and just sort of design accordingly. So it's not a very complicated thing to do. It's just a matter of having the will to do it. Next slide. When we have high groundwater, vegetation's the key. I think we're doing a pretty good job of coordinating stormwater here in the Madison area, but we can always do better. And again, we need to take a watershed approach. So with that, I can take questions.
Well, I'll wait for a few more questions to come into the chat and start off with Thanking you, Ken, for your nice presentation today. I do have a question about, you had mentioned some areas are not really suitable for infiltration basins because of high water tables. Would you say that maybe the best overall approach, most versatile approach would be a vegetated basin so that it not only captures water, but encourages high evapotranspiration as well?
Absolutely. I think we have to have, we're going to have to look at the vegetation in our systems. I think also wherever you can do roof, I was pretty negative on roof gardens years ago because I was more focusing on groundwater recharge, but groundwater recharge, the water we use in Madison is not coming from local, it's coming up from the north anyway, and that land's probably, some of that land's going to stay in farmland forever. So yes, I think we need to use more green, more plants, and they can be on the roof or they can be in the bioretention cells. But I think just having ponds that can't have maximum evaporation, I don't think that's going to work.
Okay. And we have a question wondering if the legislative change you mentioned was put in place during the Walker administration?
Yeah.
Okay. And also, although not a part of the presentation, could you discuss some of the special effects of karst topography on drainage?
Karst topography. Wow. Yeah. That's I'm not an expert on that, but I understand enough to know you've got to be really careful with that because you can create sinkholes, for example. So that's just going to take special attention to you need a geologist to interpret or to get a handle on whatever the local carbonate, how it's placed and so on and so forth, and what the risks are. So that's a challenge, no question, and that's another situation where again evapotranspiration is going to be a key.
Okay, that's it for the questions at this point. So we'll give it a minute to see if anyone else is typing a question right now.
Yeah, let me just say that, again, I'm happy to take emails or so KW Potter, all lowercase, at @WISC-EDU. And if you think of something later or if you get some good ideas, I'd love to hear them. I think there's a lot of room for creativity, particularly on the vegetation side. And so please feel free to get in touch.
All right, well, I did put Ken's email in the chat box in case anybody wants to write it down. I don't see any more questions in the chat, so thank you very much, Ken, for taking part of your time during this interesting time in history to be with us for the CLMN webinar. And the next one will be coming up just next week, so refer back to my email if you'd like to register for next week's webinar as well. There's still 4 more to go this spring. So with that, thanks everyone for joining, and thank you again, Ken, for presenting for us today.
Enjoy the day. It's going to be a beautiful one.